All right, welcome to the deep dive.
Mhm.
Today, we're going to take like a deep dive into something, you use every day, probably multiple times a day,
Mm.
but I bet you don't think much about it. And that is CMOS image sensors.
CMOS, that's right.
CMOS image sensors. Now, we're not just talking about, how your phone camera captures light or your, big fancy camera. We're really going to get down into like the nitty-gritty physics, the engineering that goes into these things.
It's going to be, it's a really interesting topic. I mean, if you've ever been curious, like how do these things work? How do they transform the world that we see into the digital images that we all use every day? This is the place to be. And we've been looking through a bunch of sources, including a really good book called CMOS Image Sensors by Konstantin D. Stefanov.
Yeah, it's a good one. And our mission today is pretty straightforward. We want to understand that basic process by which an image sensor converts light, photons,
Yep.
into an electronic signal. We're going to unpack all the key elements that go into that. We're going to highlight, some of the clever solutions that engineers have come up with to make these things work so well.
Right, it's really impressive.
Yeah. Okay, so let's just jump right into it. How does a sensor actually take a stream of photons and turn it into something your digital device, can interpret?
Well, the magic really starts with something called the internal photoelectric effect. Now, when photons, these particles of light, strike the silicon atoms within a sensor's pixels,
Okay.
they transfer energy to electrons.
Okay.
Now, this happens during a very precisely controlled amount of time, known as the integration time.
Integration time.
And during this integration time, each pixel acts like a little, well, I guess you could say, accumulating an electrical charge in proportion to the number of photons that hit it.
Gotcha.
And that's the key. That's how we go from light to an electrical signal that we can measure.
Okay, so the longer the sensor is exposed to light, the more charge builds up in each pixel.
Exactly. That's
Yeah.
right. And we want to have, ideally, this one-to-one relationship, a linear relationship, between the intensity of the light coming in and the amount of electrical charge generated. So if we double the amount of light coming in, we want to double the electrical output. That's linearity. Now, most sensors are designed to be very, very linear.
Okay.
But some actually have nonlinear responses, and they do this on purpose.
Okay.
So they can handle like a huge range of light levels
Okay.
simultaneously. We call this a high dynamic range.
Right.
It's kind of like our own eyes.
Right.
We could adapt to going from a very bright sunny day to being inside in a dimly lit room.
Right.
Our eyes have a huge dynamic range.
Gotcha. You mentioned this accumulation of charge or integration. Why do we do that? Why is that a better approach than just, trying to measure the current, the electrical current, coming in directly?
Well, it's a really good question, especially when we consider situations where there's not much light.
Okay.
The currents produced by just a few photons hitting a pixel each second, it's a tiny, tiny amount of current. We're talking about less than a single electron per second
Wow.
that we might have to measure.
Okay.
And directly measuring that tiny amount of current is extremely challenging because of all the electrical noise there is. But by letting the charge accumulate, by integrating it, we can build up a much bigger signal over a set integration time, making it a lot easier to measure accurately. It's kind of like if you were trying to weigh individual grains of sand,
Okay.
or if you weighed a whole pile,
Yeah.
the pile gives you a much more accurate reading.
Makes sense.
And pretty much all modern image sensors operate on this principle.
Okay. So we've got photons that hit the silicon and they create this electrical charge. But what is going on at the really fundamental level there?
Right.
How does a photon free an electron?
Well, that brings us to something called the photoelectric effect in semiconductors.
Yeah.
So when a photon with enough energy hits a silicon atom,
Okay.
it can excite an electron, bumping it up from a lower energy state, we call that the valence band, to a higher energy state, which we call the conduction band.
Okay.
And this promotion of the electron leaves behind what we call a hole.
Okay.
And that hole is basically like a missing electron. It acts like a positive charge.
Okay.
So one photon, when it's absorbed, can create one of these electron hole pairs.
Okay. Electron hole pair. Got it. Now, I remember reading that silicon is an indirect band gap semiconductor. Does that complicate things?
Yeah, it does add a little wrinkle. Because silicon has an indirect band gap, when the photon excites the electron, it often needs to interact with vibrations
Okay.
in the silicon crystal lattice. And these vibrations are called phonons.
Phonons.
Yeah, so it's kind of like you need a little extra push, that phonon, to get the electron to jump up to
Gotcha.
that higher energy level. And this makes, light absorption in silicon a little less efficient than some other materials like that have direct band gaps.
Okay.
But, for the photons that we see, visible light, generally one absorbed photon equals one electron hole pair.
Okay, so 1-to-1 for visible light. Now, how much energy does a photon need to have to cause that, electron to jump?
Well, the energy of a photon is directly related to its wavelength. And it's described by the equation EPH equals 1240 over lambda, where EPH is the photon energy and lambda is the wavelength of the light. Now, for silicon, the energy difference between the valence band and the conduction band, that's the band gap at room temperature, is about 1.12 electron volts.
Okay.
And that corresponds to a wavelength of about 1107 nanometers.
Okay.
And we call that the cutoff wavelength for silicon.
Okay, so anything longer.
Anything longer than that.
Doesn't have the energy to...
Yeah, it doesn't have enough energy
to bump it up.
To bump that electron up.
Okay. So shorter wavelength light, like blue light, carries more energy than like a longer wavelength like red light.
Absolutely, that's right. And so a single photon can't create multiple electron hole pairs in silicon, not in the visible range.
Okay.
But the fact that each photon in that range can create at least one allows us to calculate how much charge a given amount of light will create.
Gotcha.
Because if we know the irradiance, the intensity of the light, we can figure out how many electron hole pairs are generated per second within a given pixel, assuming that all the light is absorbed.
Okay, so there's a condition there. They have to be absorbed. Is that always a given?
No, not at all.
Okay.
The likelihood that a photon is going to be absorbed by the silicon really depends on its wavelength.
Okay.
The absorption lengths can vary a lot across the electromagnetic spectrum. For example, ultraviolet light, like 300 nanometers. The absorption length is just a few nanometers, so that means it's absorbed really close to the surface.
Okay.
But if we look at longer wavelengths, like near infrared, around 1100 nanometers, the absorption length can be hundreds or even thousands of micrometers.
Wow, okay.
But to effectively absorb those longer wavelengths, you need thicker silicon.
Okay, so different colors of light penetrate silicon to different depths.
Absolutely, yeah.
What about other types of electromagnetic radiation? I noticed in the book they mentioned X-rays.
Right, yeah.
Can they be detected by silicon?
Yes, silicon is also sensitive to X-rays.
Okay.
Though it's a little different because X-rays are much, much more energetic.
Right.
A common X-ray source for calibrating detectors, for example, is iron-55.
Okay.
And iron-55 emits X-rays that have energies of 5.89 keV, that's manganese K-alpha, and 6.49 keV, manganese K-beta.
Okay.
Now, these X-rays have absorption lengths much longer than visible light, about 28 micrometers in silicon. So in a typical optical image sensor, which has much thinner active silicon layers, only a fraction of those X-rays are going to be absorbed.
Okay, so they kind of pass right through.
To some extent, yeah, more than visible light.
Okay.
But when they are absorbed, because they have so much energy, they create a lot more electron hole pairs compared to a single visible light photon.
Okay.
So, for example, a single manganese K-alpha X-ray photon, because it has thousands of electron volts of energy compared to, the band gap of silicon, which is only about 1 electron volt, can generate hundreds or thousands of electron hole pairs.
Okay, so even though fewer get absorbed,
right,
the ones that do
have a big effect.
Have a big effect. Okay.
Right.
All right, so we've got photons that are hitting the silicon and they're generating these electron hole pairs.
Right.
What happens to those next? I mean, do they just hang out?
Well, not exactly. If we want to use these electron hole pairs to create a signal, that represents an image, those charges have to stick around long enough to be collected by the sensor circuitry.
Okay.
And this is where we introduce this important concept called carrier lifetime.
Okay.
Carrier lifetime is basically the average time that an electron, or a hole exists in its free state before it recombines with a carrier of the opposite type.
Right.
Or gets trapped by some imperfection in the crystal.
Okay.
So generally, a longer carrier lifetime is good.
Makes sense.
Because it gives us more time to collect those charges.
Yeah.
Now, the collection process typically happens in like hundreds of nanoseconds.
Okay.
And if they recombine too quickly, if the lifetime is too short,
Yeah.
then they're not going to be around to contribute to the signal.
Right. So they're gone.
Right, they're gone.
Yeah.
And that's going to reduce the sensor sensitivity.
Okay.
So we want a long carrier lifetime. Now, in high-quality silicon, what we call epitaxial silicon, the carrier lifetime can be much longer than that typical collection time.
Okay. So what causes them to recombine to get trapped?
Well, there are a couple things. The dominant mechanism is trap-assisted recombination.
Okay.
And this happens because there are imperfections in the silicon crystal.
Okay.
Now, it is possible for an electron in a hole to recombine directly, but that's not super common in silicon, not in the way it's structured.
Okay.
But more often, these imperfections or impurities act like traps.
Okay.
And those traps can grab a free carrier, either an electron or a hole,
Right.
and then hold on to it, and then later grab the opposite type, and that causes them to recombine.
Gotcha.
And then they're gone, as far as our signal is concerned.
Right. They're out of the game.
Right, right. And the rate at which this recombination happens is proportional to how many excess carriers there are.
Okay.
And inversely proportional to the carrier lifetime.
Gotcha.
There's an equation for that. U equals negative dn dt, which equals np minus np0 over tau.
Okay, so more imperfections in the silicon crystal, that leads to a shorter carrier lifetime and a weaker signal.
Basically.
Yeah. Oh.
And there are actually a few different types of recombination processes that can happen.
Okay.
One is called Shockley-Rehall recombination. That's the trap-assisted kind we just talked about.
Okay.
There's also Auger recombination, where when the electron and hole recombine, the energy that's released gets transferred to another free carrier.
Okay.
And then there's radiative recombination, where a photon is actually emitted when the electron and hole recombine. So the total carrier lifetime in silicon is affected by all these different processes, all acting at the same time.
Gotcha.
And it's usually limited by the fastest of those processes.
Okay.
Kind of like the total resistance in a parallel circuit is dominated by the smallest resistor.
Right. Okay. Okay. So we need these, electrons or holes to move to a place where we can measure them, for our signal.
Right.
How do they move around in there?
Well, there are two main ways carriers move in semiconductors. One is diffusion, and that's just their natural tendency to move from areas of high concentration to low concentration, just due to their random thermal motion.
Okay.
But then there's also drift.
Okay.
And drift is the movement caused by an electric field.
Okay.
And in image sensors, drift is the dominant mechanism for charge collection because the electric fields in the sensor help to sweep those electrons and holes towards the right spots to get collected.
Okay. So the electric field is like a guide.
That's right.
It tells them where to go.
Yeah, it directs them where they need to go.
Okay. And then what happens once they get to that point?
Well, the next big step is charge conversion.
Okay.
And this is where the collected charge gets converted into an electrical signal. Typically, it's a voltage.
Okay.
And it happens at a specific spot called a sense node.
Sense node.
Okay.
Yeah.
Now, charge conversion can be destructive, where the charge is used up in the measurement.
Okay.
Or it can be non-destructive, where the charge can be measured multiple times without being removed.
Interesting. Okay. So sense node, that's a key part.
Yeah.
What actually gathers that charge in the first place? What are those collection elements that you've been, mentioning?
Well, there are two fundamental elements we use. One is the PN junction.
Okay.
And the other is the MOS capacitor.
Okay. So PN junction first.
Sure, yeah. So a PN junction is formed when a P-type semiconductor, which has, extra holes, is brought into contact with an N-type semiconductor, which has extra electrons. And when you do that, a region forms at the interface where there aren't any of these mobile charge carriers.
Okay.
We call that the depletion region.
The depletion region. And that's where all the mobile electrons and holes are swept away.
Exactly.
Leaving a region with a built-in electric field.
That's right. And that happens because electrons from the N side want to diffuse to the P side, and holes from the P side want to diffuse to the N side.
Okay.
So as they move across, they recombine, and they leave behind these immobile ions near the junction.
Right.
And this separation of charge creates a built-in voltage across the depletion region.
Okay.
We call that VBI, the built-in potential.
Okay.
And that built-in potential is what establishes the electric field inside the depletion region.
Okay.
Now, in a simple PN junction, we call it an abrupt junction.
Okay.
This electric field is kind of triangular shaped.
Okay.
And it gets stronger as you move away from the edges of the depletion region towards the middle, where the P and N materials actually meet.
So this electric field, this built-in electric field, is what separates and collects the photo-generated electrons and holes.
That's exactly right.
Okay.
So electrons that are generated within or very close to the depletion region are swept by the electric field towards the N side.
Okay.
And holes get swept towards the P side.
Gotcha.
Now, the voltage we need to apply across the junction
Yeah.
to make the depletion region extend all the way through the active area
Okay.
is called the full depletion voltage, or VFD.
Oh.
Now, if the active layer is really thick, VFD is much larger than the built-in potential.
Okay.
And we can usually just ignore the built-in potential
Gotcha.
for our calculations. If we apply a reverse bias voltage that's even larger than VFD,
Okay.
we get something called overdepletion.
Okay.
And that gives us a more uniform and stronger electric field.
Okay.
So we can actually calculate how long it takes to collect the charge in a fully depleted PN junction, though we have to be careful. Because at really high electric field strengths, the velocity of the carriers can actually saturate.
What does that mean?
It means that they can't move any faster,
Okay.
no matter how strong the field gets.
Interesting.
So it makes some of our calculations based on constant carrier mobility less accurate.
Okay. Okay. So a PN junction naturally gives us this electric field that we need. What if we just, took a chunk of silicon, like plain silicon, and applied a voltage across it? Would that work?
That's a good question.
Would that collect the charge?
Well, if you apply a voltage across any material that has a finite resistance, and that includes silicon, even really pure intrinsic silicon,
Okay.
a current will flow, Ohm's law.
Right.
But that current would be indistinguishable from the current generated by, incoming light.
Okay.
So it would be almost impossible to isolate the signal that we're looking for.
Okay.
So to minimize that dark current, you'd need silicon with an impossibly high resistivity.
Okay. Okay. So you really need that PN junction to get that charge separated.
That's right. It's essential.
Okay. Okay. So now PN junctions use that built-in electric field in the depletion region. How does a MOS capacitor do it?
Okay, well, the MOS capacitor is another really important component in image sensors.
Okay.
It's basically a three-layer structure. You have a metal gate electrode, a thin insulating layer, typically silicon dioxide, SiO2,
Right.
and the semiconductor substrate, which is, almost always silicon.
Right.
And when we apply a voltage to that metal gate electrode,
Okay.
it can create a depletion region in the semiconductor underneath that insulator,
Okay.
kind of like the depletion region in the PN junction.
So the voltage on the gate, that's how we control whether or not that depletion region forms.
Exactly. So that voltage really controls how the charge carriers are distributed within the semiconductor. So depending on the voltage and the polarity, whether it's positive or negative, you can create different conditions in the semiconductor at the interface. Accumulation, where a majority carriers are attracted to the surface, depletion, where they're repelled, creating that depletion region, or inversion, where minority carriers are attracted to the surface, forming a conductive channel. And for image sensors, we're really interested in operating that MOS capacitor in the depletion regime.
Okay. Okay. So how does this relate to capacitance? I've seen, the book mention oxide capacitance and depletion capacitance.
Right.
What are those?
Well, the MOS structure has capacitance just by its nature.
Okay.
That oxide layer acts as the dielectric material in a capacitor.
Okay.
And the metal gate and the semiconductor, they act like the two plates.
Okay.
So that gives rise to the oxide capacitance, which is determined by the thickness of that oxide layer,
Okay.
the dielectric constant of the silicon dioxide, and the area of the gate.
Okay.
Now, when the depletion region forms in the semiconductor under the gate, it basically adds another capacitor in series with that oxide capacitance.
Okay.
We call that the depletion capacitance, or CDEP.
Okay.
So the total gate capacitance
Right.
is then the series combination of those two.
Okay. And a series combination, that means that the total capacitance is always lower than either of the individual capacitances.
That's right, yeah.
Okay. Now, when a large depletion region forms in the semiconductor, because of a large gate voltage, we call that deep depletion.
Deep depletion, okay.
Yeah. And in deep depletion, that depletion capacitance gets much smaller
Okay.
than the oxide capacitance.
So the total gate capacitance is basically just the oxide capacitance
Gotcha.
at that point. And that's actually very similar to the capacitance of a PN junction with the same width,
Okay.
of the depletion region. There's an example in the book that calculates the oxide capacitance for a silicon dioxide layer
Okay.
that's 7 nanometers thick,
Okay.
and then calculates the gate capacitance in deep depletion.
Okay.
It gives you a good feel for
Yeah.
like what these numbers actually look like.
Right. Right. Okay. So you've got, PN junctions. We've got MOS capacitors. They can both create these depletion regions,
Right.
which we need to collect our charge.
Exactly.
Now, what about transistors? I mean, we know they're important in
Yes.
all sorts of electronics. What is the specific role of a MOSFET in an image sensor?
MOSFETs, metal oxide semiconductor field effect transistors,
Yeah.
they are essential to CMOS image sensors.
Okay.
And the most critical feature is their extremely high input impedance.
Okay. And what does that mean?
Well, as we talked about, the signals in image sensing are tiny.
Yeah.
We're talking about, a few electrons per second.
Right.
That's a tiny current. And to measure that, we need something that doesn't draw much current,
Mm-hmm.
from the charge that we're trying to measure.
Right.
So we need a really good insulator.
Okay.
And silicon dioxide, which is used as the gate insulator in MOSFETs,
Mm-hmm.
is a fantastic insulator. It gives us
Yeah.
these really, really low leakage currents,
Okay.
so we can actually measure those tiny signals.
Okay.
Now, just to give you an idea, a PN junction,
Mhm.
even a really good one, would have much higher leakage currents
Okay.
than a MOSFET.
Okay.
So the basic structure of an N-channel MOSFET, it's got 3 terminals: the gate,
Mm-hmm.
the source, and the drain.
Mm-hmm.
And the source and drain regions, they form PN junctions with the substrate.
Okay, so high input impedance means that they basically don't draw any significant current
Right.
from the charge they're
Yes,
measuring.
that's exactly
Okay,
right.
okay. So MOSFETs have two main operating regions.
Yes.
Linear and saturation.
Exactly.
Right.
What are those?
Well, in the linear region, sometimes called the triode region,
Yeah.
the MOSFET acts like a voltage-controlled resistor.
Okay.
And the current flowing through it, from drain to source,
Yeah.
is described by this equation, 1.70 in the book.
Okay.
This is the mode we use for analog switches.
Okay.
Then in the saturation region, which is when the voltage between the drain and source is larger than the voltage between the gate and source minus the threshold voltage,
Okay.
the drain current becomes pretty much independent of the drain source voltage.
Okay.
And it's mostly controlled by the gate source voltage.
Gotcha.
That's equation 1.72 in the book. And in this mode, the MOSFET acts like a voltage-controlled current source.
Okay. So it can be both a resistor and a current source.
That's right, depending on how we bias it. Yeah.
Okay. Okay. I always hear the term transconductance when people are talking about transistors.
Mhm.
What exactly does that mean? Yeah, transconductance is a really important parameter for
Hmm.
MOSFETs.
Okay.
It's basically a measure of how much the gate voltage affects the drain current.
Okay.
It's represented by G sub M, and it's defined as the change in drain current
Okay.
divided by the change in gate source voltage.
Okay.
And there are equations for G sub M in the book, 1.73 and 1.74, that show how it's related to the device parameters
Okay.
and the drain current.
Okay.
But basically, it tells you how effectively you can control the current flow
Right.
with the gate voltage.
Gotcha. What about this sub-threshold operation? I saw that mentioned in the outline.
Yeah, even when the gate source voltage is below the threshold voltage,
Mm-hmm.
a little bit of current still flows between the source and drain.
Okay.
We call that sub-threshold operation, or sometimes weak inversion.
Okay.
And in this regime, the drain current depends exponentially on the gate source voltage.
Okay.
But the actual current levels are really tiny,
Okay.
usually nanoamps. So the transconductance is lower than when the transistor is in saturation.
Okay.
But this sub-threshold operation, we see a lot in circuits where a MOSFET's driving a really high impedance load, like when we connect a pixel sense node to a reset transistor.
Okay. Okay. And then what is this output resistance?
Right.
That sounds like something that you generally want to be low?
Yeah, for an ideal voltage source, that's true.
Right.
But a MOSFET operating in saturation, it acts more like a current source.
Okay.
And it has an output resistance, which is given by equation 1.82 in the book.
Okay.
And in this case, a higher output resistance
Mm-hmm.
means that the drain current's less sensitive to changes in the drain source voltage.
Okay. So it's a better current source.
Exactly.
Okay. Now, what is this body effect?
Okay, so the body in a MOSFET, it's the semiconductor substrate
Okay.
the transistor is built on.
Okay.
And the body effect describes how the voltage difference between the source terminal and the substrate can affect the transistor's threshold voltage.
Okay.
It's basically because changing that voltage changes the width of the depletion region that forms in the substrate near the source body PN junction.
Okay.
And that, in turn, affects how much gate voltage you need to create that conducting channel.
Yeah.
So we need to consider the body effect when we're designing circuits, like source followers and amplifiers,
Gotcha.
where the source substrate voltage might not be constant.
Okay. Now, going back to the MOS capacitor.
Yeah.
The